So let's go to diagnostic checking. So far, the variance decomposition shown in the ANOVA table, it has been purely numerical. The relationships among the sum of squares apply to any data set. The ANOVA is meaningful and can be used to draw conclusion if the assumed model is correct. Like we would say YTI equal to mu plus tau t plus epsilon. So we had this equation before, and this tau t, it was mu t minus mu. So under the assumption that the error of like epsilon are normally distributed, the terms in the model can be estimated from, like we would say, mu estimate is equal to y bar, tau estimate for t. I said that it's like mu of that treatment minus mu, but we are talking about the sample, so it's going to be y bar, for example. Y bar of t, mu is that when we are talking about the whole population. Y bar t minus y bar, y estimate of the ti is going to be y bar t, and then like epsilon is going to be this, like the amount for the residual. We can then examine residual plots to check the adequacy of the assumed model. So we would have overall dot diagram for all residuals, and this is the plot of the residuals. So I have we would have, for example, residuals versus the predicted value. So if there are no difference between diets, it can be shown that the mean square for between diets, like between diet A, B, C, D, is estimating the error variance as is the mean square within the diets. So this suggests that a test to determine if significant difference exists between diets can be formulated as the following F-test. So we can say the null hypothesis is that tau of A means that, okay, the mean for that we would have for treatment A minus the mean of the overall is equal to 0. Like the mean of each of these treatments, it's in fact equal to the mean of the overall mean that we have. And the alternative hypothesis, we would say at least one of them is greater than 0, so it's not equal to the 0. And so the F observed, the same things that we had for the ANOVA table before. So before we said that it's MSR over MSE for the F observed, but here in ANOVA table we have the MS of the between treatments and then MS of the within treatments. So F observed is going to be MS of the between treatment over MS of the within treatment. And the example that we had, we just divide them, is going to be 13. So you can find out the F of the from table here as well. So you know what's the denominator and what's the numerator here. So we would say F for the degree of freedom of the between treatments and degree of freedom of the within treatments. And then you would read, we can read the F, the critical value, and let's say the alpha is like 5% for this. If we select alpha 5%, F for, so between treatments, we had 4 treatments, right? So the degree of freedom for this can be 3. And then we have, for the within treatments, we would say the degree of freedom for the residual, it was 20. For finding out that one way was that you could say the total degree of freedom, which is 23 here, minus the degree of freedom for between treatments, is going to give you the degree of freedom of the within treatments, or like something inside the treatments. Or you can say that, okay, so I have 4 treatments. The first one, degree of freedom was 3. The second one was 3. The fourth one was 5, and the third one was 5, and the fourth one was, we had 8. Some observations, so it was 7. So 3, 5, and 7. We would add them, it's going to give us 20. So you can go with both methods. And then alpha is 5% from the table. We would read it, and it's going to be 3. And when we compare the F critical, like F from the table, with the F observed, we find that, oh, F observed is greater than the F from the, like the tabulated, like from the table. And because F observed is greater than the F critical, it's like that we reject the null hypothesis, in fact, right? So we are outside the null hypothesis area. We are in the rejection region. So therefore, we can reject the null hypothesis and conclude that there are significant differences between diets. So the null hypothesis was that the mean of each of these diets or treatments, individual means for each of them, they were equal to each other and they were equal to 0. And because of that, we would say tau of t is equal to 0. They were equal to the, no, they weren't equal. The difference between them and mu was equal to 0, and like the overall mu. Because of that, tau of t was equal to 0. But when we reject the null hypothesis, it's like that. We would say there's significant difference between the diets. But how are they different? So if we say that, okay, so they're different. But for comparing, to know that how are they different, so far what we did with F table, we compared 4 different treatments. So it was more than one treatment. So we compared 4 different together, right? And our treatments, they were diet, different types of the diets. So for the how are they different, but we would examine methods for comparing multiple means. Like we want to compare the, let's say, we want to say that, okay, what's that, when we say how are different like that, for example, A, B, and C. So let's compare them together to see that what's going to happen. Instead of comparing with the F test, F test just tells us that if these treatments, they are significantly different or not. Just this, like it doesn't tell us anything else. So consider, so here is that when we have the t-test for comparing them, but we call it Bonferroni t-test. So consider a set of k-means, and we would say there are k times k minus 1 divided by 2 possible pair of means and test of the type. So we would say H null is equal to the, like, for example, mu I equal to mu j, and the alternative hypothesis is that the mu I and mu j, they are not equal. So these can be tested by calculating a t-test. So we would say t observed is that the difference between their mean divided by the s times like a square root of 1 over ni plus 1 over nj. And comparing with the t from the table. And for the table, we would say n minus t. We said that for t table from the, like when you want to read the t from table, you need the degree of freedom and your like level of significance. So for degree of freedom, we would say n minus k. So we said that we have k means, right? And then it's a two-sided test. So level of significance is going to be half of the alpha. And capital N is the total number of the treatment that we have, like I t equal to 1 to k for nt. Total number of the observation, like total number of the observation from all of the treatments that we have. Performing like Bonferroni test is complicated. It's a little challenging. However, with the, like, if we're working with the softwares, it's not going to be that much hard, but we would need to do that. If you're going to do that by hand, it's going to be a little like challenging. But in addition, it has another even more serious drawback. Perform all tests at the level of significance alpha. Then so we would have alpha prime as the overall probability of making at least one incorrect rejection is much larger than alpha and is unknown. So we would have an upper bound for a set of C tests at alpha is given by the Bonferroni inequality. So we would say alpha prime is less than or equal to 1 minus alpha, like power c. And this is the Bonferroni equation. Let's, if we have a look at an example, it's going to be easier to understand it. For example, if our k is equal to 5, we would say there are, like we said, k times k minus 1 divided by 2. So it would be 10 possible comparison between these k. Like I have, let's say, 5 treatments. If I say I have 5 treatments, I can, if I want to compare these treatments, it's like that I could have 10 possible comparison. Even if each test is carried out at individual alpha equal to 5%, I would say my alpha prime, based on the Bonferroni inequality, is going to be less than or equal to 1 minus, and then I'm going to put it in the equation of the 1 minus 0.05 alpha power c. So c is equal to, like that one that I said, as k times k minus 1 divided by 2. This one is equal to c. It's the same as c. So it's going to be 0.40. So alpha prime, it's like 40%. We consider alpha as 5%, but in reality, the alpha prime, the upper bound, it can go up to 40%. This is another drawback. So alpha above stands for comparison-wise error rate, individual test of the, like, for the individual test. Alpha prime is the experiment-wise error rate. And if we go to the second year stat, we said that alpha it represents type 1 error as well. You can review it, but just know that alpha, it's in the rejection area, right? So it would just know that this alpha we can call it as the error rate as well. So if just consider this alpha prime was like k was equal to 5, we said that the alpha prime can be less than or equal to 40%. If c equal to let's say 10, so if c is equal to 10 tests with alpha equal to 1%, that was for alpha equal to 5%, right? If I change the alpha from 5% to 1%, then alpha prime is gonna be equal to the, like, 10%. So these are the things, this is a drawback that we would have. To compensate, we would only carry out those tests that are really of interest to the investigation. So let's say c is equal to, and we say that c was k times k minus 1 divided by 2, and then we would choose a reasonably small target upper bound for alpha prime, and then conduct each test at individual alpha equal to b divided by c. So we would consider upper bound and then divided by the c value that we will find.